Hello again, everybody, and welcome back. This is the beginning of our Chapter 9 chapter on linear momentum and collisions, and we're going to start right off the bat by describing what momentum is. So momentum, first of all, it's indicated by a lowercase p. Again, m is taken because of mass, and actually it has something to do with mass itself. Momentum is indicated by p, and you'll notice the arrow over the p indicates that it is a vector. Our momentum is the product of the mass times the velocity of the object that has the momentum. And since it deals with velocity, being a vector, that means that the momentum itself has direction. So an object that has a mass, which pretty much every object does, and has velocity, has some momentum, but it's in a given direction. It's in a given direction. So the direction matters. All right, you can have positive momentum or negative momentum because you've got a direction on a coordinate system, so you've got a positive or negative direction. The units are kilogram meters per second, and that should make sense because mass is in kilograms and velocity is in meters per second, so it's kilogram meter in the numerator per second in the denominator. And so if you've got a variety of objects with different masses and different velocities, you could say the total momentum for that whole system of objects is the sum of all those momenta. Now we have them added right here, there's pluses in between them, but some of these momenta, I think it's the right plural, momenta, may be negative. So if the one object has a negative momentum, you might insert a negative right there, or possibly right there. So we're going to say that the total momentum, or the net momentum, is the sum of all of them, but keep in mind that some of them may be a negative momentum based on the velocity that it currently has. So let's take a look at our Newton's second law, that is net force equals mass times acceleration. And this is true, but it's true to a limited degree. It's true when the object has a constant mass. We're assuming that this m right here, this lowercase m, is always the same, like a dropping ball or a moving object along a rail system or something like that, like a moving cart. But there are going to be objects that we deal with their momentum where the mass actually changes. A great example of this is a rocket. A rocket that is shot into space. The mass of the rocket itself changes, right? There's your rocket right there, and with the nozzle at the end. But as the fuel is expended at the end, so inside right here is where your fuel cavity is. The mass of the rocket as it leaves the ground gets less and less and less as this fuel level gets less and less in there. So kind of a more general law that we can say is that the net force is really described as the momentum over time, a momentum change over time. And so this object, as it maybe increases its velocity, all right, it's going to be decreasing its mass because the object has less and less fuel inside of it. So kind of a more general way to say Newton's law is really, we could say that since momentum is mass times velocity, m times the change in distance over time, we can say that that's really ma because we have this delta t in the denominator right here. So delta t times t. So here's our mass. Here is our velocity, right? Change in distance over time times time. That gives us our mass times acceleration because net force equals mass times meters per second squared. Or I should say, mass is kilograms. Kilograms, that's our m, and there's our a. So that comes from momentum change over time. So the object's mass is changing, that is accounted for by the momentum. So even if the mass varies, we can figure out what the net force is on the system based on how it's moving, not using ma, but by using the more general change in momentum over change in time. The reason that we talk about this is because this kind of contributes to the second idea, the second main concept that we want to talk about in this chapter, and that is the idea of impulse. Impulse, as indicated by a capital I, is a vector quantity, but because it's made up of other vector quantities that we're already familiar with. we can say, we say that impulse is the average force applied on an object times the amount of time that it's applied over. All right, and so for a given impulse, the greater the time that it's applied, the less the force that is going to be. Or the less the time, the greater the force is going to be. Since these are multiplied together to give our impulse, as one increases, the other decreases, and so forth. But the reason that our previous equation of net force equals our change in momentum over change in time, that should be a lowercase p right there. What that does, that allows us to define impulse as this. So if our average force, for now we're just kind of equating it to our net force, if that is change in momentum over time, and if impulse is that force times time, then that means that the times cancel out. So this in the numerator and this in the denominator go away. And so impulse is really described as our change in momentum. So change always means, change is always final minus initial, right? So we can say that that is mass times velocity, put our vector arrows there, mass times velocity final minus mass times velocity initial. That is really what we describe as impulse right here. And that's based off of our definition of momentum and assuming that we could write net force as being the change in momentum over the change in time. This is called the momentum impulse theorem. And so think of it like you may have seen, I don't know, martial arts masters as they break boards, maybe even they break cinder blocks or something like that with a chop, from the side of the hand. What they're doing is they're applying a force over a very, very small time. I didn't mean to scratch that up right there. Over a very, very small time right here. And so as the time decreases, the force increases, and so that force applied to the board or to the cinder block is going to be very, very great. What that means is they need to change the momentum of their hand very, very rapidly. As they contact the board, they've got to change the direction of their hand so that the force applied is very, very big because the amount of time that it is applied is very small. All right, we're going to be applying some examples of this in the next few problems, and a good example of this is that of baseball. When a batter, whether it's baseball or softball, contacts the ball with their bat, okay, it is in contact with the bat with a very, very short period of time. All right, that ball touching the bat. Now this is a very high-speed camera picture right here, but it's not very long that the ball is touching the bat. So the ball comes in, all right, with some mass times velocity, and then it leaves with another mass times velocity final right there. And so that impulse, the force applied by the bat, times the amount of time that it is applied, a very, very small amount of time, the impulse is very big. And so it results in a major change in momentum of the ball. As you've seen, if you've seen a game of baseball, the ball changes direction very, very rapidly, and so it changes its momentum very, very rapidly. One thing to point out is that this average force right here, we use this as our force multiplier because if you've ever seen a very slow motion, maybe a video or set of frames of a ball contacting a bat, it touches the bat and then it compresses down and then it reaches a point where it can't compress anymore and then it uncompresses and the ball kind of shoots off in the opposite direction. What that means is the force that's applied is variable. It's very little force, and when the ball is totally compressed, it's maximum force, and then it's uncompressing and the force is getting less and less again. The force that we're using in these equations is the average force. So right about in here would be the average force, a little bit less over here, greater over here. The average force is what we use to multiply to find out what the impulse is on this ball that is being contacted by the bat. And this right here is just a more close-up version of the same thing. All right, so this average force that is applied results in a momentum change on the ball over time. The smaller that amount of time is, the greater the force is for a given momentum change, and so the ball is going to rapidly accelerate away from the bat. So that's going to be at the end of our first little segment here on momentum and our definition of momentum and impulse. Momentum being the product of mass times velocity, and impulse being force times time, also known as the change in momentum. So what we're going to do is stop right there, and then I'm going to wait till the next segment to start our first example and see if we can apply this, and maybe it'll make a little bit more sense to us. So thanks for following along, and I'll see you on the next one.